Ray, and hello everybody. Thanks a lot to the organizers for this opportunity, and I'm sad not to be there in person today. Yeah, so we're going to be talking about particles near vortices, and and all the time I'm going to be talking about Lambosine vortices. And why am I talking about Lambosine vortices? So this slide is to make the case for that. So here is a two-dimensional turbulence simulation done by Rashmi. What she did here is start with some noise for the initial vorticity and run now 2D Navier-Stokes. And you see that in 2D turbulence, vorticity organizes itself into these pretty circular patches, and if you cut any of those patches like 1 and 2 over here, the profile of the vorticity is pretty Gaussian. So most of the time vortices like to be Lambosine vortices in turbulence. Of course, like on an average, they may not be, they're stretched, they're doing funny things, and they may not have a circular cross section because of the influence of each other, but a Lambosine is pretty standard, and you can therefore call it the Drosophila of turbulence in the way that Drosophila is used in biology to stand in for other organisms. So that's the Lambosine vortex. Today I'll be talking all about 2D. I will not talk about 3D except to say that we've done some studies in 3D, and a lot of what I'm going to say in 2D carries over to 3D, maybe even better. Now we have these vortices which are Lambosine vortices, and the particles which we throw around in turbulence follow the Maxi-Reilly equation. They are in one-way coupling, they're in dilute suspension, and these particles are very small, have very small Reynolds number compared to the fluid. So they are in Stokes flow, except they have an inertia. So spherical particles obey the Maxi-Reilly equation, and that's what we'll be talking about. V is the particle velocity and U is the fluid velocity. So this is a complicated expression, but we'll be using a simplified version, except in the end we'll discuss Bassett history. So the case I want to make today is the following. It's about how droplets grow in clouds. So we know that there is this thing called the droplet growth bottleneck. So when cloud droplets are smaller than 10 micron, they're known to grow pretty fast by diffusion, by just condensation happening on aerosol particles. And when they're like pretty big, like more than 50 or 100 microns, they grow pretty well by gravity, like big droplets fall faster than small droplets, and they collect those small droplets as they go down and they grow. So how do raindrops grow from here to here? And usually turbulence is given as the answer for bridging this droplet growth bottleneck, and preferential concentration, which we'll see in the next slide, is often offered as the argument. But we will see that this can only happen if the Stokes number is already big. That means the particles are already like rather several tens of microns. So like we want to propose today this thing called single vortex caustics for bridging the droplet growth bottleneck. And we'll see what this is and why we think it bridges the bottleneck. We'll resort to this fact that turbulent intermittency has very strong small scale vortices. So we know about the hunt for caustics. A lot of people have been looking for caustics. So what are caustics? It's when, so for example, in this paper by Bewley et al., you'll see that there are two big vortices and teeny particles are getting centrifuged out of these vortices. So we know that inertial particles get centrifuged out of vortices and they form voids near vortices. So then when this happens, let's say from these two vortices, two particles are coming and they're dashing against each other, they're colliding against each other. That is called caustics, because at the place where they collide, the particle behavior cannot be described as a field. At the same point, you have two different velocities. At the same space and time position, you have two different velocities. So those are called caustics. So normally when you talk about caustics, you talk about particles coming out of different vortices. whereas we are going to be talking about particles coming out of the exact same vortex. So here's our Lambosine vortex. Then there is this pink circle of particles and the black circle of particles, and we'll call the situation caustics when the pink circle overtakes the black circle. So at a given time, the pinks are moving faster than the blacks and they're colliding against the blacks. That will be our caustics. So then we studied this particular case of one vortex and two rings of particles several years ago. In fact, Ravichandran, who's now in IIT Bombay, studied this problem in great detail. And he studied heavy particles. We'll talk about lighter particles way down in the talk. And for these particles, when you neglect Bassett history, the Maxi-Reilly equation can be written in this extremely simple form, where you have V minus U, the difference between particle and fluid velocity, and 1 over Stokes number, and that gives the acceleration of the particle. So this is a very simple equation. When you write this equation in cylindrical coordinates just around a vortex, and you scale it by this length scale, special length scale, where tau is the particle time scale and gamma is the circulation of the vortex. So when you make this length scale and you write down, and tau is the time scale we use, you get this parameter free set of equations. That's the beauty. So like you solve these equations, now they are valid, the same answers are valid for any vortex, any Stokes number. So the equations are parameter free. And we ask, when can the pink circle overtake the black circle? And that is another way of saying, when and where do caustics happen? So we find that caustics can happen only if the initial radius of the pink and the black, when they're starting very close to each other, only if their initial radius is pretty close to the vortex, namely it's less than 0.55. Within this regime, these rings can overtake each other. Outside this regime, and it's 0.55 in this length scale. Outside this regime, there is an outer solution which is very simple to solve. They just create Fermat spirals and nothing very dramatic is happening. And there the flow can be described as a field. Now, when you have such things, so like here we have a Lambosine vortex, just to show you that a lot of collisions can happen, and because of that, coalescence and particle growth can happen when you have caustics particles. So here inside that special magic radius, we color the particles green. Outside the magic radius, we color the particles red. And when you run this movie, all the particles who have a little bit of green blood in them, those particles are colored navy blue. And we can see that as the particles, come out of the vortex, we can see that only the navy blue particles are really big. That means only caustics particles are really big. So this gives you the importance of caustics. Caustics are very important for collisions and coalescence. And so in this droplet growth bottleneck problem, we need this single vortex caustics. That's the case I'm going to make. And here you'll see that if you have 1 in a million lucky drops in a cloud, that means 1 in a million drops are somehow much bigger than others in a cloud, then this is well known to be enough for this rain initiation to happen. So like, how can rain initiation happen? It's when we want to say that it's when you start out with particles all of very teeny tiny Stokes number, and 1 in a million of them can participate in these caustics events. And if they participate in single vortex caustics, they can grow big enough, and then they can create rain. So the question is, can single vortex caustics provide as many as you need, namely 1 in a million? For this, what we need to understand is that in turbulence, whenever you have a powerful vortex, you have these particles centrifuging out, and you have a void region inside in the neighborhood of the vortex, and all particles agglomerating outside the vortex. So this inner solution that I talked about is valid in this region. So like outside you have all the particles collecting, and inside there's a void. So whoever used to be in a void has a big chance of colliding with somebody else. That's the basic message. So we want to understand void volumes in turbulence to understand how many such lucky droplets there can be. So here we're talking in the context of a cloud, but it will be valid for any other situation where there are particles. So now the first thing we know is that there is this special caustics radius given by this quantity. And the first thing is that the vortex itself, which is shown to be very small here, and the void region is shown to be very big. The first thing we need for this void is that the RV, the vortex radius, should be smaller than the particle radius. So, sorry, smaller than the caustics radius. So if the caustics radius is bigger than the vortex, like shown here, that's when you get a void. Otherwise, you do not get any significant void. So here are all these red vortices, which are big, and the yellow caustics radii, which are small. So these cannot participate in any rain initiation or special collision events, whereas such particles can participate in collision events because they have some void created. So this is the basic message. Now in real turbulence, how do we calculate the void? So like here we're talking about homogeneous isotropic turbulence without thermodynamics. Life is much, much better when there is thermodynamics, but we haven't completed that study with 3D, so I can't talk about it. But here we have this beautiful analysis of homogeneous isotropic turbulence at fairly big Taylor microscale Reynolds number made by Dhaval Bhuaria and Alain Pumer. And this paper has been a saving grace for us. Like, it's been a way to calculate whether or not a cloud can have enough lucky droplets for rain initiation from single vortex caustics. So what we do here is we go and look at their data. Here they plotted the probability density function of the square of the magnitude of the magnitude of the vorticity as a function, the probability density of this thing, and it's scaled by the Kolmogorov time scale. And they show this at different Reynolds numbers. You see that as the Reynolds number becomes very big, you have very many very powerful vortices whose time scale is very short. So they're going to rotate around very fast, and their vorticity is very, very big. So these are the very powerful intermittent vortices we need for caustics to occur. So like knowing this and knowing their study where they've given sizes, they've given all kinds of scalings and all kinds of collapse, we can actually make a table. And the table tells us that our void volume, this is kind of the critical void volume you need for the 1 in a million. And this tells us that you need at least a Taylor-Reynolds number of 1300 for rain initiation. So we can stick our necks out and say we need Reynolds number of 1300 for rain initiation, whereas cumulus clouds are actually at a much bigger Reynolds number, so they have a good chance of rain initiation. Now, basically, here we've said that here is a Reynolds number. For this class, we've used cloud values for droplet density, number density, everything. And we've estimated when you can have enough caustics droplets for rain initiation. Now we're going to stop with this heavy particle, and we're going to talk about lighter particles. And here we're going to talk about a special thing called the Bassett-Boussinesq history. I told you earlier that in the Maxi-Reilly equation, we're neglecting that term. For heavy particles, we get kind of lucky. We can neglect this term and not make a very big difference to the answer. But suppose the particles are finitely heavy. Suppose they're heavier than the fluid, but their densities are comparable. Then Divya and Sauma, they're present PhD students. Divya will be over there in a few days. So they have carried out this very nice study of what happens to particles which are finitely heavy and what happens when Bassett history comes into play. So now the Maxi-Reilly equations for such particles are a little more complicated. Q is the relative velocity V minus U. We can write the Maxi-Reilly equation in this form, and you see that there is this horrible history term with, square roots of time in the denominator, and, to compute this thing, this integral every time is hugely computationally heavy. So like that's why most people neglect the pink term, whether it's negligible or not. And we're going to show that it's not negligible for finitely heavy particles. So like here is a Stokes number we define based on the Lambosine vortex radius, and R is a finite, it's a number defining the finite thickness. Now I'll skip this thing, but I just want to say that we have a very nice method, which is Vishal Vasan's idea of solving for the Bassett history without enormous memory and enormous time costs. So I will encourage you to look at that. So we use that method for this thing which we call a particle necklace. So what have we done here? We have a vortex whose thickness is RV, and it's shown here. So R is on the x-axis in these movies, and V, the velocity of the particle, is on the y-axis. So, and this is the vortex thickness. So we start a necklace of particles, like, this whole line is full of particles arranged like that. And we ask what happens to this necklace as the vortex spins around, and like whether caustics can form. So like we have a finite density ratio of 14. The particles are 14 times denser than the fluid, and we start this big necklace here. You can see at 0 time, yeah, that's the necklace. And every time you have a multivaluedness in R, that is caustics. So these things.
Rama, just actually a question and a comment that you're down to the 3 minutes. But what does color represent on the necklace here?
Okay, the color just represents the initial location.
Initial
so
position.
Just to remember where it was initially, we color it. So blue inside and red outside.
Okay.
So you see like caustics forming, and you see that there is some difference with Bassett history, especially in terms of the number of collisions that happen. And these are the number of collisions with time that we've plotted. And so you see multivaluedness and you see this thing. Now we reduce the density ratio and you see something quite dramatic happening. So instead of that simple caustics that was forming, you're getting these loops in the particle necklace, and in every loop, so like you see triple valued caustics, like 3 particles dashing at a given time. All kinds of such things happen. And here you see that when you include Bassett history, a lot changes. So this loop thing, the loop thing is quite different with Bassett history. These loops last longer and they go on to a further distance. So the effect of caustic stays for a longer time, but the caustics are less violent than without the Bassett history. So for lighter particles, we need to use Bassett history. That's the moral. And the particle collisions, the place where they collide and the time at which they collide, goes through some very interesting peaks and valleys. So this is the central message that Bassett history can be important here. And I'll end my talk with the summary that caustics can form within a special radius near a single vortex, and they are consistent with the creation of lucky drops in clouds. So like we can explain how rain initiation can happen by using this concept of caustics near a single vortex. And when you have lighter particles, you can have a lot of interesting types of caustics which are long lasting. So thanks for your attention.
Thank you so much, Rama, for this interesting talk. We'll open it up for questions.
Hi, Rama. This is Natalie. I had a question about your last slide, where you had the interesting loops. When you look at your pictures, would you mind going back for a sec?
Yeah.
Yeah, this one. If you look at the spectrogram on the right-hand side, or I don't know if you call it a spectrogram, you see some kind of time signal which is indicative of the kind of loop frequency, right? So can you say something about that? What is the significance of that, like, kind of repeated signal, and where is it coming from? How does it scale?
Okay. So basically, you see that, these loops are at a certain distance from each other. And wherever there are loops, there are caustics, and wherever there are caustics, there are collisions. So like in these loops, there are things colliding and these loops are moving downstream. And that's why you see these peaks and valleys. And they have a particular frequency, but it's not very periodic, as you can see. It's a nonlinear set of equations, so it's not completely periodic. And with Bassett history, it becomes, in fact, like not even a dynamical system. So we can't really talk about simplifying it further than this. Does that answer your question, Natalie?
Yes, yes, it does. Question?
Hello, Rama.
Right.
I have a question about the on this particle necklace and the and computing the history term, which is the Bassett force. What is I see that the density of the particle is pretty high. So I guess what is the Stokes number for this simulation that you've done?
Okay. So we've done this with a variety of Stokes numbers. I wish I'd written down the Stokes number. That's a bad flaw. But this is around 0.1 is the Stokes number. It's not very small.
0.1.
But one thing I'd like to say is that in turbulence, the Stokes number can be very, very small based on the typical time scale. But based on a vortex time scale, you can have a very high Stokes number, because the vortex is spinning around at a much faster than Kolmogorov scale.
Yeah, but
So
there was another slide before when it was much, and then the difference in density was much larger, huh?
Yeah.
Here, I guess the Stokes number is much larger, no?
Yeah, no, in both of them, we kept the Stokes number the same. So the Stokes number is a different non-dimensional parameter. So like the Stokes number is given by this quantity and the R, which is the density ratio, is given by this quantity. So we separated the density ratio from the Stokes number.
Yeah.
The Stokes number.
And are you sure that the equation is holding for this large Stokes number? Because basically this Bassett-Boussinesq-Haussine equation has been derived for small Reynolds number, and the kernel in the history force is use the Stokes drag. So as soon as you have a little bit for higher inertia, I mean, this Bassett term will fail. I mean, it will not be correct.
Yeah, that's a very important point. The point is that we have small enough Stokes number that things are valid, but we don't always have small enough Reynolds number. So like, you know, when they're just starting out at this location, we find that the Reynolds numbers are of order 10. So like there we have a problem. But once the thing comes outside the vortex, these Reynolds numbers are very, very small.
Okay.
So then here we are quite safe, but in the initial part, so especially in this, like those initial loops, I wouldn't give too much. I wouldn't, you know, lay my reputation on those.
Thank you.
Hi, here's Eberhard. I have a question on what are the consequences on the interparticle distance or radial distribution function, any measure you take on instantaneous distribution functions that you would measure in the flow?
Sorry, what are the consequences of the radial?
On the radial distribution function or any type of clustering that you would expect in the flow? So if you measure a real cloud, what would you expect?
Okay. So like wherever there is a vortex and, you know, wherever there is a caustics radius, I'd find a sudden jump in the radial density, number density. So if you measured, you know, number density as a function of radial distance from the center of a Lambosine vortex, at the caustics radius, you'll find a big bump, and that bump will slowly move outwards.
Move outward in time, or?
In time, very slowly in time, yes.
Okay, thanks.
Thank you.
Thank you, Christopher speaking. I have a question regarding the equations that you were solving. So in the last transparent, you showed that you had particles that were slightly more dense than the fluids. But do you include also added mass forces in the equations
Yes.
you're solving?
Yes.
Okay.
We've included the added mass. It's maybe I haven't written it clearly, but yes. Yeah, the added mass is here.
Hi.
There is a half density, and that's included in this term.
Hi, thanks for your talk. I just had a little question. One of the videos you showed of the particles in the Lambosine vortex just visually kind of struck me as looking a little bit like a planetary accretion disk. I know that problem is not totally dissimilar from rain forming in clouds. So I was just wondering if you've thought about how or if this work might be useful to astronomers studying that sort of problem.
Yeah, so I feel that that's definitely worth exploring, but I don't know the answer. Maybe Jeremy knows better. But yeah, the thing is that this kind of thing should be effective there as well, because you have a mean spin which is like a vortex. So like I'm sure that some effect of caustics should happen there as well.
Thanks, Rama. This is Eckhart. I was wondering, maybe I missed it. Did you look at density ratios of 1,000? And are there any new effects that show up at those very large density ratios?
We looked at density ratios of 1,000 with and without Bassett, and there the effects are smaller.
Mm-hmm. Okay, thank you.
Yeah, so whereas if it is 10 or something, then the effects are pretty big, even though 10 is a big number.
There's time for one more question, I think. Christian?
Thank you for an interesting presentation. So we have looked at kaustic formation in fluctuating flows, and there we find that for small Stokes numbers, caustics form in regions where you have a large strain and no vorticity. So I wonder if you have considered other flow regions. So why did you look at the vortex regions, and have you instead looked at strain regions, and what kind of kaustic formation did you find in those regions in that case?
Okay, so we haven't studied strain regions so much. Like we were particularly interested in centrifugation, and which is why we looked at caustics near a single vortex. And typically, in order to have the strain region caustics, you need the Stokes number based on the mean time itself to be large. Whereas we wanted to understand rain initiation where all the droplets are so very teeny tiny that only centrifugation from a single vortex could do something. So that's why we were interested in that. But I have been looking at some recent papers. I don't know whether they're yours, based to ask about, how those criteria for caustics carry over to our case. And we actually got a caustics radius based on those criteria, which was order 1. So like I think there is some consistency to that.
Okay, thank you so much. Let's thank Rama again.